comments. So today I'm going to discuss about chapter 10, and then after chapter 10, I'll discuss about anything else you want, any other questions. But basically, in chapter 10 was about columns or compression members. So for columns or compression members, again, we have obviously a column that has some sort of load. In your particular class, we're only looking at loads that are centric loads, so along the centroid. And there are times when the column will buckle, and there are times when the column will not buckle. So basically, up to a certain critical point, below this, we can use our normal stress is equal to P over A. Above this, we have to figure out, we can use our critical stress by the formula here for the buckling. So we have pi squared, modulus of elasticity in over this, what's called a slenderness ratio, L over R. So we have L, obviously the length, and as the length gets longer, it has more tendency to buckle. And the R is not radius, the R is what's from this, the moment of inertia is the area times the radius of gyration squared. So in this case, it's the radius of gyration. So you would take I over A and get R squared. So basically, if you have a small dimension in this way and a long dimension the other way, we're going to tend to have the buckling behavior. So this behavior rather than the other behavior. And as you see, those two cross at a certain point. This particular case, it's 89, but it's only 89 because we have a certain yield stress and we have a certain modulus of elasticity. If you use a different modulus of elasticity, let's say we have aluminum instead of steel, that would have a different yield stress. You would get two other things. So basically, there's two key formulas. One is the critical load. The other one is the critical stress. And obviously, you can find the critical stress if you just use this formula and divide by A at the end, because basically it's the same thing. So there's a few key points in chapter 10. One is the end conditions. So the end conditions, this is something you should memorize because it's not on the final exam, is this concept of effective length. So there's different end conditions, and those will cause a different effective length. So basically, the effective length is some multiplication of the regular length depending on the end conditions. So for the first case where we have one fixed condition, so the fixed condition means basically we cannot rotate at that particular point. It has to stay perpendicular to the support at that particular point. And in this particular case, it's free. So free means that there's no reactions, either moment or force reactions, that this basically is free to move back and forth. It's also free to rotate. So there's no moment, there's no forces. So in this case, it's 2L. And if you just sort of look at it, this is sort of looks, again, this is what I said in the lecture, twice the length of the regular one. The pins at two ends is sort of the most common general case. So pins at both ends mean that we have reactions at the pins, but there's no moment at the pins. So again, it can rotate, but it can't translate. So it can't move up and down, it can't move left and right, but it can rotate. So you can see this rotation at either end. And all those pin connections are the same. So here we can rotate. All the fixed ones are also the same. We cannot rotate. So if you sort of look at this case where both ends are fixed, it's sort of the most optimum condition for allowing the maximum load, because our effective length here is only half of the length, and our allowable P is pi squared E I over effective length squared. So basically this number gets bigger when we have different end conditions. The other key thing to remember is in many cases you have to check both planes. So we can buckle in either two planes or two axes. So your book again uses two different terminologies. One is buckling in a plane. So buckling in an XY plane would be the same as buckling about the Z axis. Buckling about the XZ plane at the bottom would be buckling about the Y axis. So the key thing here is to sort of look at your coordinate system. In this particular case, the coordinate system is a little bit different than other cases. Here they have X is the long axis, and then Y and Z are the sort of transverse axes. So for the XY plane, if we look at the side view, so we're looking at the view of this side here, the plane that's in X and Y, we have something that looks relatively skinny. It's A on this dimension, and then it's B back and forth. We obviously have our load applied here. And the other thing is looking at the end conditions. So one is making sure you look at both planes. The other one is you look at the end conditions. So you can sort of see at B, we have a fixed end. So it doesn't matter which plane, it's fixed in both ends. So in this particular case, we have a fixed end here. And then you have to sort of read the problem to figure out what's happening. So in this particular case, it says two smooth and rounded fixed plates restrain end A from moving in one of the vertical planes in symmetry, but don't allow it to move in the other plane. So if you look at this, and let me erase a little bit of the scribbles here. If you look at this, basically on this axis, you can see that that whole thing can sort of move in either way. It's not restrained in any way. But in the other way, it cannot move because you have these two things, these rounded things that don't allow it to move. So it can move along Z, it cannot move along Y. So in the XY plane, we're looking at the XY plane. It has these two supports here. So it cannot move back and forth. However, because it says they're smooth and rounded, you're assuming that it can rotate. So this basically acts like a pin. So in the XY plane, you can see we used the fixed pin effective length, and we also used the moment of inertia. So in these problems, typically in the exam, like the problems are not that long, but most students don't use the right moment of inertia or the right end conditions. So there's only really four things to this problem, or the two planes, but there's, an axis of the moment of inertia, and there's then the effective length. So make sure you use the right ones. So you can see here we have b a cubed. So the in this particular case, we're taking the moment of inertia about z. So the moment of inertia about z, meaning that the h and the, well, for the bh cubed, you have a different thing on either side. So basically the key is to make sure you use the right thing. So this is solved in your book. This is a sample problem. And the other one is just, again, the same kind of thing, the end conditions and the moment of inertia. So in this particular case, again, reading the problem is key. So this cable are basically, they prevent motion in the XZ plane. So if we look at this again, we have the XZ plane is basically this plane in this particular problem. So these ropes, they're tight, so they don't allow it to move backwards and forwards. So then this acts as a pin. So if I draw a side view here, this is the sort of the dots for the web underneath this part. This end is fixed, as you can sort of see here. And at this point, this, because of the ropes, this acts as a pin. So this is a pin, and this is a fixed. And then you need to take the right moment of inertia. So again, this is the X, Z plane. That means we take our moment of inertia about Y. So for the other one, the other side, I'll just get you down here really quick. We have these little things for the flanges here. We have fixed here at this end. And then this one is free. And use obviously the correct effective length, and your moment of inertia would be your moment of inertia about X in this particular case. And then obviously knowing this chart, make sure you always look at your axis system may be labeled differently, but look at this in relationship to your diagram. So whatever these axes are, you're either taking a moment of inertia about this axis or the other axis. So obviously this is what the x-axis is. From this is the x, and obviously this is the y. And you can sort of see, if I compare any one particular case, we have a strong axis and we have a weak axis, and the weak axis is generally 4 or 5 times weaker. So one axis is going to buckle for sure in one direction. I'm going to stop recording.